The title of today's lecture is The Myth About Einstein. In common perception, Einstein comes out as a strong mathematical physicist. This is, however, a myth. Even in 1905, Einstein was very close to real-life phenomena. This lecture presents how he used simple mathematics to understand experiments, especially on Brownian motion and photoelectric effect, employing the underlying concept of thermodynamic fluctuations. The popular image of Albert Einstein, mostly drawn from his portraits at a somewhat ripe age, is not merely that he was a dreamy-eyed, long-haired, and a bit absent-minded scientist, but that he was very strongly mathematically oriented. This perception of Einstein is bolstered by his work on the general theory of relativity in 1915 that impacts on our universe and the cosmos, which not only pose challenging issues to trained physicists, but also conjure up in the minds of the uninitiated a sense of distant vastness, almost bordering on mysticism. In pursuit of the general theory of relativity, Einstein did actually master covariant and contravariant tensor analysis, as propounded by the stalwart mathematicians Gauss, Riemann, and others, and did become an expert on many aspects of geometry. This resulted in the departure from Euclidean geometry and heralded the birth of fascinating new ideas of space-time geometry. It is this development which has perhaps led to the commonly perceived vision of Einstein. But the point is, and that point is going to be a recurring theme of this presentation, that Einstein employed mathematics merely as a tool in developing a new structure of a theory, not so much to make new contributions to the subject of mathematics itself, but to understand the phenomena of gravity and gravitational fields. The above perception of Einstein in the popular mind that he was a powerful mathematical physicist whose work was beyond comprehension of ordinary mortals is one myth that I would like to dispel in this set of lectures. Indeed, as we come to discuss the 1905 Einstein, we'll discover that the mathematics Einstein used was actually very simple, within the realm of understanding by present plus 2 students. Einstein's primary focus was to elucidate natural phenomena as evident in everyday life and as seen through experiments. Given this background, let me turn attention to two of Einstein's stupendous contributions in the year 1905, the photoelectric effect, which fetched him the Nobel Prize, and Brownian motion. What you can see in figure 1 is a schematic illustration of how, by shining light on a metallic plate, an electric current can be generated from the ejected electrons, whereas figure 2 depicts an application of diffusion emanating from the theory of Brownian motion in simulating kanji script on the surface of copper with the aid of diffusing atoms. What is the remarkable commonality between the Brownian motion and the photoelectric effect is Einstein's usage of Boltzmann's idea of statistical fluctuations. In our discussion on these two topics, I'll try to pinpoint where Einstein makes ingenious application of the concept of thermally aided fluctuations that give rise to the classical equipartition theorem of kinetic theory. Now, let me turn to Brownian motion. Here I describe Einstein's work preceded by his doctoral thesis, which was submitted on 30th April 1905 but published later in 1906. The thesis is a remarkable exposition of Einstein's contact with real-life phenomena. It's a description of a new method for Avogadro number determination and also the calculation of the size of a molecule. It is incredible today to imagine that something like molecular reality which we take for granted as a concept, found no consensus amongst physicists and chemists in as late as the 19th century. Einstein's PhD thesis deals with bulk rheological properties of particle suspensions and contains results with an extraordinary range of applications relevant to 1. Construction industry, based on what has now emerged as a novel interdisciplinary subject of granular matter. 2. Dairy industry, through the colloidal suspension properties of, for instance, casein micelles in cow's milk. And ecology, involving the Brownian movement of aerosol particles in clouds. On this, Abraham Pais writes in his most readable biography on Einstein called Subtle is the Lord. Einstein might have enjoyed, I'm quoting from Pais, might have enjoyed hearing this since he was quite fond of applying physics to practical situations, unquote. I now turn attentions to Einstein's thesis, in which he produced two separate, ingeniously developed ideas that led to two separate relations between capital N, the Avogadro number, and small a, the radius of a molecule assumed to be spherical. Our first concern is what is called the renormalized viscosity, which we will denote by eta star. The point is that suppose I have a solvent, let's say water, which would have a bare viscosity, call it eta. Now if I add sugar as solute particles to water, we expect the viscosity to increase. What Einstein considered was the increase in the viscosity, and the new viscosity is what he called eta star, would be in fact greater than eta by a factor which will be linearly proportional to the density of solute to the lowest order in the density. That is, he considered very dilute amounts of solute in solvent. Now, therefore, like all practitioners of the art, Einstein considers a simple model, a region of solvent containing, as I said, dilute amounts of solute whose molecules are much bigger in size than the solvent molecules, as depicted schematically in figure 3. How big are the solute molecules? Well, the radii are smaller than 10 to the minus 3 millimeter, which in today's parlance translates into 1000 nanometer, and hence it is relevant to mention how critically important Brownian motion is in the contemporarily significant topic of nanoscience. The system at hand, as I said, could be a dilute solution of sugar molecules as solutes dissolved in water as solvent. Einstein then makes a reasonable assumption that the bare viscosity eta of the solvent, upon mixing with solute, must be enhanced, it is increased to a renormalized value eta star. As said before, where the fractional increase must be proportional to the volume of the solute per unit volume of the solvent. Therefore, we have equation 1, where eta star over eta to the lowest order would be equal to 1, but the correction term would be proportional to the volume of the solute particle, each solute particle, which is 4/3 pi a cubed, a being the radius of the solute molecule, multiplied by the number of solute particles per unit volume of the solvent, and therefore that number is given by the Avogadro number n divided by the mass number capital M multiplied by rho, where rho is the mass of a solute particle per unit volume of the solvent. So remember this point, rho is not the density of solute per se, but it's the mass of a single solute particle per unit volume of this solvent. So it is very easy to understand the reason behind the factor n over m times rho, because if the molecular weight of the solute is m, it means that m grams of the solute will contain an Avogadro number capital N of solute particles, right? Therefore, each solute particle would weigh m over n grams. So in this expression, m over n will occur in the denominator, and then you multiply by rho, and remind you again that rho is the weight or the mass of the solute per unit volume of the solvent. So mass and mass would cancel out, and what you have is actually 4/3 pi a cube divided by per unit volume of the solvent. So that's the correction term of eta star over eta. Einstein then makes use of the experimental data on eta star and eta for sugar solutions, and knowing capital M and eta, he therefore determines the product n times a cubed. However, the catch is that we only get a relation where n and a occurs in a product form. So how to decipher either n or a, and for which he needed another equation. And that is where he produced this brilliant thermodynamic plus dynamic argument, which is stated below. So as I said, Einstein considers a very dilute amount of solute in the solvent. So consider again the region of figure 3 and consider that the fluid is in motion. It is never meant to stop at any finite temperature, and we therefore rely on the original picture of Robert Brown, where you may recall that he considered pollen particles, flower pollen particles in water, and water is at constant temperature capital T, but as you know, the equipartition theorem says that even at any temperature T, there's a mean square velocity, so the water molecules are in incessant motion and they bombard the pollen particles. As a result, the pollen particles themselves undergo a random zigzag motion, which is what is called the Brownian motion. So assume for simplicity, which is what Einstein did, that the motion takes place in one direction, call it x. So solvent is therefore expected to provide, because of the thermal kicks, a push to the solutes, and that push will generate a force. So if F, that's an internal force, it's not an externally applied force. And this, therefore, if F is the resultant force on each solute particle, the force per unit volume of the solvent will be F multiplied by the same factor that we encountered before, namely capital N over M times rho. So that will be like force per unit volume of the solvent. Now if you remember that your pressure is force per unit area. So we have on the right hand side force per unit volume. So that determines therefore what is called the pressure gradient, as is indicated schematically again in figure 4. So that's how we get equation 2. Now Einstein takes recourse to Boltzmann's concept of thermal fluctuations and making the bold assumption that the solute particles are so dilute that they should behave as the molecules of an ideal gas. He writes for the pressure P equal to RT divided by M times rho. As you know, this is Boyle's and Charles' law, where capital R is a gas constant, T the temperature, capital M again is the molecular weight, and rho is the density of the solute per unit volume of the solvent. So that is a very drastic but bold assumption that the solute particles behave like an ideal gas system. Once you have this expression for the pressure, you then go back to equation 1, and then you get an equation for what you may call the density gradient, d rho dx, because dp dx will give you d rho dx is given by equation 4. So notice that this equation is linear on the right hand side in rho, which is what the theory is restricted to. The linearity in rho has to be maintained. Einstein then moves from thermodynamics to a fluid dynamic argument and said that because the only force present in the liquid is the viscous force, which is given by Stokes' law, F must be equal to what is given in equation 5, where the minus sign takes into account the fact that the viscous force always opposes the direction of motion, which is given by the velocity v. And Stokes said that force has a magnitude given by 6 pi eta a times v itself. So at this stage, the student may raise the question, why on the right hand side of equation 5 it is eta and not the eta star, the denormalized viscosity, that appears? If you go back to equation 1, you see that eta star will have an eta term and a term which is linear in rho. So if you now then put eta star in equation 5 instead of eta and plug in equation 4, you will get a term of the order of rho squared, which Einstein neglects. So the theory again is restricted to very dilute amount of solute per unit volume of the solvent. So it is only linear in rho, and that is why it is eta that appears on the right hand side of equation 5. Okay, so far so good. Then Einstein makes another brilliant assertion that when a fluid is in motion, then there is of course a density gradient, and that density gradient determines what is called, to the equation of continuity, what is called the current density. And the current density is given by rho times the velocity itself, and that is obtained from what is called Fick's law of diffusion, which is given by equation 1. So phenomenologically, it says that rho times v is minus the diffusion coefficient d times the density gradient d rho dx, d being the diffusion coefficient, as I said. Okay, so now you see this equation is actually very familiar to you from electrodynamics, because the left hand side of 6 is like a current density, and if you remember Ohm's law says the current density is the electrical conductivity sigma times the electric intensity of the field, and the electric intensity E itself is negative of the gradient of the electrostatic potential. And so this equation 6 is analogous to Ohm's law, where capital D plays the role of the electrical conductivity sigma, which is a measure of the mobility. In the case of electrical conductivity, is the mobility of positive or negative charges, and capital D is now a measure of the mobility of the solute particles, and d rho dx is the analog of the change in the electrostatic potential per unit distance. Miraculously then, when you substitute equation 6, three quantities drop out. F drops out, rho drops out, d rho dx drops out, and we have a compact relationship of the diffusion coefficient given by equation 7, where d is equal to RT divided by 6 pi eta, with the viscosity, times n times A. Incidentally, this equation in the same year, 1905, was interestingly given by an Australian scientist called Sutherland. Be that as it may, we restrict our discussion to Einstein's work. So we have now a separate expression for eta times A, given that, of course, you know capital D and the other quantities. So assuming that D is known, which is what will be our next lecture session, you can estimate what is eta times A. Earlier you had an estimate from viscosity, the expression for eta A cubed. Einstein eliminated A and got an expression for capital M, which he found to be 6.6 times 10 to the 23, which is indeed very close to the presently accepted value. So in the next lecture, we will now go on to discuss how did Einstein come to an expression where it will allow you to measure the diffusion coefficient D. We now turn our discussion to the determination of the diffusion coefficient capital D. 11 days after submitting the thesis, appears a paper by Einstein on the Brownian motion in which he provides a mathematical formulation of the physical ideas already embodied in the thesis. Consider again one dimension x in which n is a function of x comma t, t being the time, measures the number of suspended solute particles per unit volume around x, that is between x and x plus dx at time t. Because the total number of particles is conserved, n of x comma t must obey an equation of continuity, much like the equation of continuity for charge conservation that you may be familiar with in electrodynamics. That leads to equation 8, where the partial time derivative of n would be given by the negative of the spatial derivative of the current. Since n is proportional to the density rho, the right hand side of equation 8 also obeys the same equation as in equation 6, yielding what is called the diffusion equation. See, what we are doing is, for n times v, you substitute what is given by the Fick's law, and that then leads to equation number 9 on the right hand side. So that's called the diffusion equation in 1D. It has an immediate generalization to higher dimension, in particular to 3 dimension, where the second order derivative with respect to x will be replaced by the Laplacian. Now in 1 dimension, this equation with free boundary conditions. I emphasized free boundary conditions, which means that n of x comma t must go to 0 as x goes to either plus infinity or minus infinity. It should also go to 0 if the time t goes to infinity, and given these boundary conditions, we end up with the familiar solution of equation 10. Familiar because you might have seen that gives you a Gaussian in x. So the point is that if you then, let's say, drop some speck in water, it will spread like a bell-shaped jar, and that's by the diffusion process. Clearly, equation 10 has the following initial condition, that if I go to the limit of t going to 0, you see if t goes to 0, the prefactor of equation 10 would go to infinity. However, the exponential function would ensure that as t goes to 0, you get an e to the power minus infinity, and that goes to 0 very fast. So the net result is finite, and that is inscribed by having a delta function in x, the Dirac delta function, because if I integrate n over all x from minus infinity to infinity in the equation 10, I should get the number n, which is what is ensured by the delta function of x, because if you remember that the Gaussian with the prefactor square root 1 over t has the limit of a delta function x as x goes to 0. This also satisfies the normalization condition that if I integrate over all x as is given in equation 12, I get the net density n, which is a constant. So from this equation 10, which is a Gaussian, we can immediately write down an expression for the mean square displacement. It's like calculating the second moment of a probability distribution. So mean square displacement is given by the integral in equation 13, which you can easily carry out by partial integration of equation 10, and the net result is a familiar diffusion equation. Mean square displacement is 2 dt as given in equation 14. So what is remarkable about this equation? is that suppose I have Newtonian motion, then of course the mean square displacement would go like t square, because the mean displacement goes like t and the mean square goes like t square. But now the mean square displacement goes like t. So, this is the aspect of the analysis, that while the thesis dealt with the macroscopic aspects of diffusion, equation 14 puts it in the proper perspective of fluctuation phenomena. Why do we call it fluctuation phenomena? Because you see, mean square x is related to the mean square fluctuation of x, because you can write mean square x as the average of x minus x average squared. And if x average squared is 0, you simply get the fluctuation as x squared average, which is also sometimes called the variance in this context. Furthermore, if we insert the expression for d that we arrived at in equation 7, we get this quite a remarkable result, that mean square displacement x squared is rt divided by 3 pi capital N eta A times t. The remarkable aspect of this is that this is the first statement in 1905 itself of what is called the fluctuation dissipation theorem, which is one of the cornerstones of what we call non-equilibrium statistical mechanics. What is the meaning of fluctuations? As I said already, that the left-hand side of equation 15 is, it enshrines all fluctuation properties of x, while in the right-hand side we have viscosity in the denominator. Viscosity is like friction, and friction leads to dissipation. So the left-hand side of equation 15 is fluctuation, the right-hand side relates to dissipation, and so this relation is called the fluctuation dissipation theorem. Point is that any given thermodynamic system, in order to reach equilibrium, necessarily must encounter dissipation. Like, for instance, you are familiar in the context of the Drude law of electrical conduction, that if you put a battery on, the current eventually would go to a stationary state where the charge carriers undergo incessant collisions, and in that case the collisions could be with defects, or it could be other disturbances like lattice motions. And as a result, you have a resistance in the material. Resistance leads to dissipation, Joule's heating. So therefore, all thermodynamic equilibrium properties, asymptotically stationary state properties, would have to be facilitated by the presence of dissipation. Dissipation is a necessary condition for a system to have a possible equilibrium or a stationary state. So apart from this theoretical nicety, equation 15 provides also a fantastic operational aid to computing the Avogadro number n, because you prepare a set of small spheres, be it of sugar molecules or of polystyrene or whatever. Use a stopwatch and a microscope and keep measuring mean square x. The result would yield n factorial. The result would yield the Avogadro number capital N. Correspondingly, if you go back to equation 14, that equation provides you a measurable avenue for the diffusion coefficient. You can do the stopwatch experiment, start measuring x square average for over many repetitions of the experiment, and you then divide by 2t, go to the limit of t very large, and the outcome is the diffusion coefficient, which is then actually was used by Einstein in estimating the Avogadro number from our earlier equation of 7. So we stop at this stage, and in the next lecture we will show you that Einstein simply did not halt at that diffusion equation. He actually laid, through Brownian motion, the foundation of a stochastic theory of diffusion. So this is what we will discuss in the next lecture. As we mentioned earlier, Einstein did not just stop at the diffusion equation 9. He laid the foundation of the stochastic theory of Brownian motion by giving a new interpretation to this equation in terms of what is now called a Markov process. This was based on a simple assumption that the suspended particles move independently of one another, as was surmised by Robert Brown himself, and again justified because of the dilution involved. That is, the solute particles are so diluted in solvent. This means that if the density of particles within the region x and x plus dx grows from n as a function of x and t at time t to n as again a function of x but at a later time t plus tau, where tau is an incremental change which is much smaller compared to t, the growth must be at the expense of the density at the preceding step. The preceding step, if each step size is assumed to be parameterized by capital delta, that the preceding step is in fact at x minus capital delta, where capital delta is much smaller than the magnitude of x. And so the density at the preceding step will be measured by n as a function of x minus delta comma t. Therefore, n at the point x at a slightly later time t plus tau would be related to n at the preceding step x minus delta at the time t through the integral equation 16, where you integrate over all probability of distributions, all possibilities of capital delta. So phi of capital delta d delta is the probability that a particle, i.e. a solute, is displaced in an interval tau, that is between t and t plus tau, and is displaced between capital delta and capital delta plus d delta. That is, the particle would lie anywhere within this range d delta. You note that the independence of particle motion is tacitly incorporated in writing probabilities in a multiplicative form under the integral in 16. Namely, n itself is a probability, phi is another probability, and the net probability is therefore a product of the two if the two processes are independent. The probability phi of delta is expected to have the plausible properties. It must be normalized, that is, if I integrate over all possible delta between minus infinity to infinity, I should get 1. And the motion must be symmetric. That is, as much as I go into the positive direction to x plus capital delta, I could equally move to x minus capital delta, and therefore phi of delta must be the same as phi of minus delta as incorporated in equation 18. So this is basically a physical assumption that the jumps are symmetric, which is actually reminiscent of what you may know as a random walk in one dimension if the walker moves in an unbiased way. That is, the walker can move to the right or to the left with equal facility. With these expressions, we may then Taylor expand phi of delta on the right hand side of 16 in space as well as time and stop at the second order, and the outcome is equation 19. So we Taylor expand the left hand side also, that is n of x comma t plus tau will be n of x plus tau times the partial of n with respect to t. Here we stop at the first order in time, and then we expand also phi of delta and n of x minus delta in Taylor expansion, and then you in fact get, when you expand n, you get this quadratic term where the linear term, which is of first order in capital delta, will drop out because of the symmetry condition in the preceding equation. So plugging in equation number 17 once again by demanding that phi of delta integrated over all delta will give to unity, we arrive at the diffusion equation 9, but now the diffusion constant d has a new interpretation. Earlier, the diffusion constant was given as mean squared displacement x squared divided by 2t over macroscopic space. But here, we relate d to a microscopic parameter, which is the step size delta, and the expression now is that d equal to 1 over 2 tau integral minus infinity to infinity del square phi delta d delta. And so now tau is the microscopic tau, which is the mean time between two jumps if you incorporate the random walk-like picture, and del square average as given in the integral equation 20 is the mean square jump length. So this microscopic formulation of diffusion, in which the coefficient of diffusion is obtained from something like a random walk type argument of a tagged particle, provides a nice link through our earlier equation 9 to the macroscopic diffusion of a region containing a cluster of particles. Let me expand this point. See, earlier, just as you assume in gas phase studies in kinetic theory, you assume that you have a number of particles within a dense volume, and so that allows you to define a number density. That is, the number density is the number of particles per unit, a volume region. And so earlier what we considered is how that region itself diffuses to the solvent. Now you change the picture. The way the region diffuses is that each particle of that region also diffuses, and it undergoes a random walk. So that's the microscopic process, and that process leads to equation 20, and lo and behold, of course that's what you expect, but it's very physically intuitive that you have the same diffusion coefficient capital D governing the equation number 20 as well as the macroscopic diffusion equation or the mean square displacement as given earlier in equation 14. This is therefore rather remarkable. It's interesting to reflect on what Einstein himself thought of his paper on Brownian motion. In 1915, the year in which he worked out the general theory of relativity, Einstein writes, quote, and this is from Abraham Pay's, "The theory of Brownian motion is of great significance since it permits an exact computation of the Avogadro number. The great importance as a matter of principle is, however, that one sees directly under the microscope part of the heat energy in the form of mechanical energy," which is to say, unquote, which is to say that, you see, the heat energy is what is responsible for the incessant motion of the solvent particles kicking the solute particles, and the mechanical energy gets reflected in the form of the viscous force. And then later on, 4 years afterwards, in 1917, Einstein further muses, quote, "Because of the understanding of the essence of Brownian motion, suddenly all doubts vanished about the correctness of Boltzmann's interpretation of the thermodynamic laws." Once again, in the words of Abraham Pay's, quote, had I to compose a one-sentence scientific biography of Einstein, I would write, better than anyone before him or after him, he knew how to invent invariance principles and make use of statistical fluctuations, unquote. In the last set of recordings, we discussed Brownian motion, and the ideas of which are still actually vigorously alive today in myriad branches of science dealing with the condensed phase of matter, biology, and material science, in particular nanomaterial science. They have also opened new vistas to basic issues concerning, for example, non-equilibrium statistical physics and quantum aspect of Brownian motion. Before we end this topic and get into black body radiation, I just want to mention that perhaps there was an incorrect statement earlier about the meaning of the Greek symbol rho. The correct statement is that rho is the mass of a collection of solute particles per unit volume of the solvent. It is not the mass of a single solute particle, which might have been inadvertently said. So rho is actually the mass density of solute particles per unit volume of the solvent. I now turn my attention to black body radiation, which, as you see, is also another contribution of Einstein in 1905, which was strongly influenced by Boltzmann's idea of statistical fluctuations. For this, we now turn back to the year 1900, when Max Planck proposed his celebrated formula for the energy density of black body radiation. Indeed, the Planck formula is the essential starting point in our effort to understand and appreciate Einstein's path-breaking contribution to the photon and the photoelectric effect. In figure 5, I have sketched what may be called a black body. The energy density, or the energy per unit volume as a function of the frequency nu of radiation and temperature T, is shown in figure 6. And can be written by the celebrated Planck formula, where E as a function of nu is given as a constant alpha, whose meaning will be clarified later on, times nu cubed divided by exponential another constant gamma nu over temperature T minus 1. The basic point of Planck was that the formula 21 interpolates between the low frequency, where E of nu will go like nu squared, which is in figure 6, and that is attributed to Rayleigh genes, and the high frequency, where E of nu goes like exponential minus gamma nu over temperature, and this was earlier discovered by Wien. So Einstein looked at these two limits separately. First, if we consider the high temperature limit, which is somewhat like a classical limit in the modern sense, we can easily derive E of nu, because you can see that in the denominator there will be essentially a temperature dependent contribution, and the E of nu now will be proportional to simply nu squared, which actually is, as we said before, is a Rayleigh jeans limit. So Einstein then went on to make the brilliant argument that the black body radiation must be viewed as an ideal photon gas. Again, the idea of ideal gas law is coming into the fore. And so if it is governed, the photon gas is governed by the ideal gas law, the energy must be also dictated by the equipartition theorem of kinetic theory. Therefore, each mode of the electromagnetic field of the black body cavity must contribute an energy kBT, where kB is the Boltzmann constant. And since the number of modes of frequency nu per unit volume is 8 pi nu square over c cubed, which was already known from Maxwell's theory of electromagnetism in almost 45 years ago, before Einstein's work, where c is the speed of light, Einstein concluded that E of nu must be equal to 8 pi nu squared over c cubed times kBT. So you see again, you note that in writing this result, Einstein was using the thermodynamic fluctuation of energy. So that's a recurring theme in not just in black body radiation, but also Brownian motion, as we discussed earlier. So this alternate form of E of nu in equation 23 allowed Einstein to immediately compute the ratio of these two constants alpha over gamma, which occurred in the Planck radiation formula. We find that in terms of the fundamental constants Kb and C, the ratio alpha over nu is given by 8 pi Kb over C cubed, and you can easily estimate by plugging in the values of Kb and C what the right hand side is, and it turns out to be about 1.26 times 10 to the minus 46 in CGS units. From high temperature, if we now go to the low T limit, Einstein then looked at E of nu and concluded that that must be nearly equal to alpha nu cubed exponential minus gamma nu over T, where the denominator in the earlier Planck expression plays an important role. So in fact, this you can view as an alternate definition actually of the inverse temperature T, because you can take a logarithm of both sides and get an expression of 1 over T in terms of E over nu. But then you take recourse to the second law of thermodynamics, where T inverse is given by ds dE, the latter being the partial derivative of the entropy per unit volume, or the specific entropy with respect to the energy epsilon. So again, you see how much thermodynamics influenced Einstein. So once you have this result for partial derivative of entropy with respect to E in terms of E, you can integrate that expression and get an expression for the specific entropy, which is given in equation 27. Now, you see, again, the two constants gamma and epsilon are occurring in this result, and so Einstein determined the integration constant in equation 27 by first converting the left-hand side of 27 into an equation for the extensive entropy, and equating the reference entropy for a volume V0 to S0, he derived that S minus S0 must be equal to total energy E, where total energy E, capital E, is epsilon times the volume, and then in terms of logarithm of the total volume V divided by the reference volume V0. Finally, if you remember, there is this famous Boltzmann relationship where the entropy is related to Kb times log of the number of phase space volume, or the probability distribution. He then used that result to write S minus S0 in terms of this probability of configuration of n photons in a volume V, which is what the black body is. And that's how he arrives at equation 29. Now, for a photon gas, the probability of configuration is basically V times V times V n number of times, because these photons are assumed to be independent of each other. There's like ideal gas molecules, and therefore the probability is multiplicative, and hence W is V to the power n as given in equation 30. And then you combine with equation 29 and get a result of S minus S0 equal to n times the n being the number density again, and then Kb is the Boltzmann constant times log of V over V0. So if you now compare this equation with the earlier equation 28, you surmise that the total energy E over gamma times nu is NKB, or energy is quantized, is given by n times gamma Kb times nu. So then you have this remarkable energy quantization formula that E must be equal to NH nu. So gamma is determined in terms of what is called the Planck constant, and therefore so gamma is essentially H divided by the Boltzmann constant. So you see the energy E that appears in equation 34 is now the thermodynamic energy. Now thermodynamic energy is a macroscopic energy, and as you know that thermodynamics hinges on microscopic basis of what is called statistical mechanics. So the total energy capital E must be the average or the thermodynamic average expectation value of the total Hamiltonian operator H given in terms of the angular brackets of H over H. Consequently, N in the earlier equation 34 must also be regarded as the average photon number that is given by the expectation value of an operator capital N, where capital N is the number operator. Historically, and because we are in Bengal, it is important to mention that it is in the unraveling of the angular brackets that takes us from thermodynamics to statistical mechanics, i.e. from the macro world to the micro world, comes in the great contribution of Satyendranath Bose. While Einstein looked at the Planck formula from the reference frame of the macro world, Bose's work made possible the further conceptual jump into the micro world and the discovery of a new statistics. But that is a different story for another day. The remarkable feature of Einstein's work on the photon is that in one shot, he broke away from the shackles of Maxwell's concept of light. That is, light is a wave that exhibits interference, diffraction, and polarization. Einstein discards this notion of light as wave and in a sense resurrects the corpuscular idea of Newton in treating light. In making this bold step, Einstein was of course guided, as he inevitably was in the year 1905, by experiments. The experiments of Leonard in 1902, which revealed that the maximum electron energy ejected from a metal due to impinging light showed quote unquote, not the slightest dependence on the light intensity, unquote. That led to the famous equation E max, that is the energy maximum, is h nu minus phi, where phi is the work function of the metal, which forms the cornerstone of the photoelectric effect. Speaking of this equation, Millikan in 1915 states, quote, I spent 10 years testing that 1905 equation of Einstein, and contrary to all my expectations, I was compelled to assert its unambiguous verification in spite of its unreasonableness, since it seems to violate everything we know about the interference of light, unquote. Millikan further deduced from his experimental data the value of the Planck constant H to be 6.4 times 10 to the minus 27 erg-second. You see, therefore, what we emphasized earlier, that Einstein was actually calculating numbers like all mortal scientists would like to do. He calculated the Avogadro number n, and his theory of the black body radiation enabled Millikan to estimate the value of the Planck constant. So taking these two papers of Einstein on Brownian motion and the black body radiation in juxtaposition, we obtain a glimpse of the trinity in Einstein's world, which is given in schematic version in figure 7, light, matter, and heat. Light consists of particles called photons, which are responsible for the photoelectric effect. At the same time, the photons constitute the black body radiation within a cavity, which is at thermal equilibrium, determining spectrum of energy levels associated with atoms and molecules of the cavity. Thus, light gets related to heat, as can be seen more clearly to the work of Satyendranath Bose and the Bose-Einstein statistics of photons, in which the temperature plays an essential role. On the other hand, light is also electromagnetic waves described by Maxwell's equations, which in turn are invariant under the Lorentz transformation of the special theory of relativity, which is also something that Einstein worked on in the same year of 1905. So from light to heat, we connect to Brownian motion, which is a result of random motion in a fluid generated by spontaneous thermal fluctuations due to heat. Thus, heat leads to damping through viscous forces which impinge on matter. Matter is something that we study in mechanics, but material motion is not only influenced by heat, as in Brownian movement, but also by light due to a phenomenon called radiation pressure. Thus, complete the circle of Trinity. Incidentally, radiation pressure is also a subject to which another great savant of Indian science, Meghnad Saha, made invaluable contribution. In conclusion, therefore, we now say that young Einstein was very, very close to experiments. He was deeply influenced by Leonard's measurements on the photoelectric effect, Brown's observations of random motion of suspended pollens, the viscosity data in sugar solutions, and so on. And he was interested in computing numbers, such as the Avogadro number and the Planck constants. This brings us to point out one very significant attribute, not often widely appreciated, of Einstein's 1905 contributions. They were all motivated by phenomena, as we begin to recognize more in analyzing his treatment of the Brownian motion discussed earlier. The second lesson is about Einstein's open-mindedness in embracing ideas and concepts from apparently distant fields. This is what is the crux of multidisciplinary research. Thus, even though he was concerned with the elementary particle of photon in his analysis of the photoelectric effect, Einstein was constantly borrowing methods and concepts from Boltzmann's thermodynamics, as elaborated in earlier discussion. Similarly, he adapted the ideas of hydrodynamics, then in the domain of chemical engineers, to his treatment of the Brownian motion. Finally, we should also learn from what turns out to be the hallmark of Einstein's approach, his unflinching boldness. Even though Maxwell's electromagnetic theory was well entrenched in terms of the observed wave phenomena of interference and diffraction, Einstein shows rare courage in its complete repudiation. Interestingly and intriguingly enough, the same Maxwellian theory is resuscitated by Einstein when he turns later in the same year of 1905 to the special theory of relativity. Well, that concludes our lecture series on Brownian motion and blackbody radiation leading to the photoelectric effect. Thank you.